My name is Charles Parker. I'm the VP of Machine Learning Algorithms at BigML, and today we're going to be talking about the new optimal resource. And what is the optimal resource? Well, at its core, the optimal resource is something that helps you to do parameter optimization. And what exactly does that mean? Parameter optimization is the process of choosing the best model and the best parameters for the data that you have. And so the core problem we have when we try to do machine learning is this. There are lots of algorithms and lots of different possible sets of parameters you could use to parameterize those algorithms. And we don't have time to try even close to all possible algorithms and all possible parameter sets, right? There's an infinity of possible algorithms and possible parameter sets out there, and we definitely don't have time to try them all. And so if only we had some way of being able to predict how an algorithm and a possible set of parameters is going to do on your data before we actually had to try it, right? So we don't have to try this infinity of things. We only have to try some small number, and we can just predict based on that small number how the rest of the parameter sets are going to do. Well, hey, we have a way of making a prediction, right? I mean, come on, we're machine learning. This is BigML, we're doing machine learning. So why can't we use machine learning to actually make a prediction of the quality of a set of parameters before we actually go through the trouble of doing the modeling and doing the evaluation on those parameters? That way we won't have to try everything. We'll just have to make predictions about whether or not something will work. And then we'll only try the things that we really think are going to work well. And so you might have had this idea, and pretty much every grad student who's been through an ML course has had this idea. And so you're in pretty good company if you've had this idea. And so this is what the webinar is going to be about. First of all, we're going to talk about the technology that underlies Optimal. How do we help you do this? How do we help you choose the best model for your data? Just because we can select a good model for you, and just because we can parameterize that model appropriately for you, it doesn't mean that you, the human, are completely out of the loop. There's still things you have to worry about, even when you're using a technology to automate parameterization and selection of your model. And so those are the things I'm going to talk about. And importantly here, these last 4 bullet points are things that always come up when you're doing model selection in machine learning. It doesn't matter whether you're doing it in an automated way or you're doing it by hand. These are always things you have to worry about. And so that's kind of the point of this little webinar, is we're going to introduce this technology, but also we're going to talk about the remaining things, the things that you, the user, have to take care of, the things that the algorithm has no way of knowing. Those 4 things are metric selection. First of all, we need to define a metric that will tell us whether or not a model is better than another model. The next thing is the dangers of naive cross-validation. So by default, Optimal and most other things will evaluate your model via cross-validation. There's times when that doesn't work. And those times, again, are particular to the sort of data problem that you have. We're going to try to make you aware of when that might happen. The next bullet point down there is selecting the best model. So once we know how to evaluate our model, we've selected a metric, we've decided whether or not we're going to do cross-validation. It might seem like a kind of an easy thing to choose the best model among all possible models, right? But this isn't trivial. You don't always want to just pick the model with the best performance. Sometimes there are other concerns. And again, whether or not you have to worry about those things is really dependent on how you're going to deploy this model in the real world. And then finally, even if you do everything right, there are still a few little gotchas that I just want to mention briefly at the very end of the presentation. Okay, so let's begin with the technology. As I said, the technology underlying Optimals is something called Bayesian parameter optimization. We've talked about this in previous webinars. This is the same technology that underlies our deepnet search. And the idea here, kind of the thing we're trying to work our way around, if you want, is that the performance of an ML algorithm and some set of parameters for that algorithm is going to be data dependent, right? It's going to be dependent on the data that you give it. Some algorithms may work very well on some data sets, and those same algorithms with those same parameters might not work very well on other data sets. To get around this, what we're going to do is we're going to try to learn from our previous attempts, right? We're going to try a few things. So let's train a model and then evaluate it just on some random set of parameters or something that usually works pretty well. And then after we've done this a few times, we've tried a few of the usual suspects, we learn a regression model to predict the performance of future models. So we don't have to try everything. We've got a little bit of data. We build a machine learning model that will make predictions on the rest of that data. And then we'll use the model that we build to choose a promising set of next models to evaluate. So instead of just randomly groping in the dark, now we have some idea of what works on this data because we've already trained a few models. And so we can use that to select our next set of models and basically repeat the process. So it looks something like this. You have this queue of parameters and model types that you want to evaluate on the left there. And then you have this block called model and evaluate, which is basically hold out some of that data, do cross-validation on this set of parameters and see what kind of performance you get out. So if we do that with our first set of parameters, let's say our first set of parameters corresponds to a deepnet, and we get performance of 0.75, however we want to define that. And then we look at our second set of parameters, and that happens to be a logistic regression, and that performs a 0.56 performance. So, not as good as the deepnet. And then, hey, we train an ensemble, and that does 0.92 performance. So that's pretty good, right? And so now, obviously, on the right here, we have this data set, which is a set of parameters is our input, a model type, and its associated parameters. That's our input in this machine learning data set. And then our objective is this performance, the thing that we're trying to predict. And so we can use machine learning to make that prediction. And basically, we can feed this back into our queue. And you can see here, we've reordered the things in our queue a little bit based on what we think is going to work based on our predictions. There's a little more cleverness here than just picking the thing that we think is going to perform the best, because we also want to make sure that we try things that we haven't tried before. So it does us no good to try, 100 ensembles that all basically look the same. We want also a variety of things that we've tried to make sure we haven't left any stone unturned, so to speak. So there's a trade-off, the classic trade-off in some machine learning settings, the trade-off of exploration versus exploitation. You want the thing that you think is going to be best, but also you want to explore the space to make sure you have a good idea of where the best thing is at. There's a few other tricks underlying this technology. First of all, we use meta learning to select a good set of initial candidates. We don't just grope completely in the dark. We use things that have worked well on other data sets. And then also, because cross-validation is expensive, right? You have to learn 5 or 10 models and do 5 or 10 evaluations. There's no reason to do it for the models that perform bad initially. So we have some sort of early stopping so we don't waste time cross-validating models that you will never bother with. And so if we look in the interface, here's a kind of toy data set. This is a churn data set. What this data set is it's patterns of usage for people who have a cell phone, the number of minutes they've used, the number of times they've called support in the last month, the amount of their bill last month, if they visited the support website. And then the variable at the end here, churn, is whether or not they left the service at the end of the month. So you're trying to predict based on their usage patterns, whether or not they're going to leave the service. And to do optimal, it's dead simple. All you have to do is go to the one-click Cloud Action menu and go down to optimal. And you'll see it works pretty much as any other BigML resource, except here you're going to get this progress update that tells you how many models it's trying. Here it's created 20 things so far. You can see the various types of models that it's creating as it's in progress here. You'll notice that this takes a little bit longer, right, than training a single model or a single ensemble on your data. This is, of course, because it's trying hundreds of different things, right, to make sure you've got the best thing. So again, the amount of time this thing is going to take is going to be, 10 minutes, 15 minutes, 20 minutes, or, if you've got a huge data set, maybe a few hours. It's not going to be the same time as the time you get from just learning, the time it takes to learn a single model. That seems really easy, right? You just click that one button and you're pretty much done. No, that's not true. There are still things you have to worry about. When you just click that one button, we try to make assumptions that work well for data sets in general. But the assumptions that work well for data sets in general might not be true of your data set. And there's no way we can really know whether or not some of these assumptions are correct. You really have to tell us. And the first one of these assumptions is metric selection. So before I get to that, what we're basically talking about here is that we need something that will drive that search, right? In the little graphical display I did back here, you see we have these performance numbers. what are those performance numbers? What are we measuring here? It could be any number of things. It could be area under an ROC curve, or it could be the phi coefficient, or it could be accuracy. By default, we choose something, but there might be something that works best for your particular data set. The caveat here is that even if most metrics are pretty correlated, right? A good model by one measure is usually a good model by most other measures, but sometimes they're not. There are cases where a particular metric disagrees with the other metric. And those cases, happen. I wouldn't say the majority of the time, but they happen often enough where you need to be thinking about it. And so if you do try to choose the right metric by hand for your data set, you can see we're progressing nicely here. I'm going to duplicate this column here so I can go back and show you the configuration panel for this data set. So we're back to our churn data set here. And I want to show you the configuration panel for optimal. So if you do choose to configure specific things about the optimal, you go to the gears icon up here like you do with all other model types. And you can see the optimal is kind of an anytime algorithm. So if you have more time, you can give the search more time. By default, it's going to try to stop within a half hour or so. But again, if you have a huge data set, or if you have a data set in particular with a lot of text fields, for example, things that are very complex, you can crank that time up and you'll probably get a better result from the search. But most of the technical things that you might need to worry about are under this optimization panel here. And the first one we're going to talk about is this optimization metric. And you can see there's a bunch of things. If you're not a technical person, you might not know what these are. There's a lot of choices here. And so if you're a little bit confused if you want to make a selection and you're a little bit confused about what metric is best for your data set, this is a little flowchart that might come in handy. The first thing you want to ask yourself is, are you going to bother to set a threshold, as we talked about in our last webinar? Are you going to set a threshold so that the probability of a certain class has to reach that threshold before you'll actually predict it? If you don't, then you ask yourself if your data set is imbalanced. If it is, you might want to use one of these metrics that controls for data set imbalance, like the phi coefficient or the F measure. If your data set isn't imbalanced, then you can just optimize for accuracy. The other side of the flowchart here is a little more complex. So the first thing we want to ask is this a ranking problem? What do we mean by a ranking problem? Well, a good example of a ranking problem is trying to pick stocks properly. So typically there's a universe of maybe 5,000 stocks that you can pick from, and you're only going to buy 10 or 20. And so the goal is to create a ranking where those top 10 or 20 stocks are the ones that you want to buy, or the ones that are most likely to make you money. So this is a ranking problem, right? A bunch of instances come in and you have to pick the ones at the top, or if you have to pick the ones at the bottom, you have to choose amongst that group of instances using your classifier. So if you do have a ranking problem, there are certain metrics that are good at evaluating data sets that are particular to that problem. Medical diagnosis is a good example of one that isn't a ranking problem, right? It's not that a batch of points come in and you need to choose a bunch of people that you want to diagnose with the disease. Each person is kind of atomic, and you want to make sure that you get the diagnosis right for that person. So this is not a ranking problem, the medical diagnosis example. If it is a ranking problem, then you might want to ask yourself if you care more about the top ranked instances in the ranking. In most cases, you do, right? So for example, if you're talking about customer churn, it's possible that you do care more about the top few people. Why? Because you want to make sure you contact the top few people that you think are most likely to churn in order to, try to convince them to stay with the service, give them some sort of promotion or so on and so forth. A good example of something where the importance isn't top heavy is if you've got a selection, some kind of selection problem where it's like a draft, where you don't know whether or not you're going to pick the top thing, or maybe you don't get to pick until the middle of the order, or maybe you don't get to pick until towards the bottom of the order, but you've got this group of things, you're going to get to pick one at some point, you just don't know which one you're going to be allowed to pick. And so the idea here is that when you produce a ranking, you want to make sure the whole ranking is good. You've made as few mistakes as possible so that no matter where you have to pick in the order, the highest thing in the ranking is the one that you're most likely to want. Contrast that with the stock picking example, for example, where it doesn't matter, once you get down to a certain point in the ranking, 100, 200, 300, 400 down, it's not like you're going to buy that many stocks, right? You're only going to buy the top, dozen or so. If you're an investor, you're not going to invest in hundreds and hundreds of things if you're trying to pick stocks. And so mistakes in the bottom of the order or towards the bottom of the order don't matter nearly as much as mistakes near the top of the order. And so again, going back here, that's all about picking this metric, right? Depending on what the problem you have, depending on the nature of the problem, how you're going to deploy that model, how you're going to use the predictions, you might want to pick a different metric here. We go with maximum phi coefficient by default because that's in recent research, that's something that happens to correlate well with almost everything else. So if we don't have any more information about your problem, if you don't want to select a specific metric, it's good to go with maximum phi coefficient because it tends to correlate with a lot of the other metrics. Okay, next up is the dangers of naive cross-validation. So by default, you can see that for our evaluation method, we use cross-validation, which is fine. Cross-validation is something that we use. It's something that almost everybody else uses. It's a good way of conducting an evaluation. And you can see a little schematic of it here. Basically, if you don't know about cross-validation, the idea is that you'll hold out part of the data and train on the rest and then test on that part that you held out. And you'll do this a number of times, to make sure that you just haven't gotten lucky with your first evaluation or something along those lines. So cross-validation is good, right? You hold out some random subset of your instances, you use those for test data, and then you do that with each chunk of your data. And again, the important thing here about cross-validation is that these chunks are randomized, right? You don't hold out one class from your data. The data that you're holding out is just a random set of points from within your data set. So it's a good tool some of the time. I might even say most of the time, cross-validation is a good way to predict whether or not you've got a good model. But there are a lot of cases, and it's not a negligible number where it's disastrously bad. And by disastrously bad, I mean, it'll tell you that your model is better than it really is. And that's sort of the worst case when we're evaluating a machine learning model, right? We don't want to hear that the model is better than it is, because then we have confidence in the results, we take it to production, and it's broken. And so this is why we offer this option for a specific holdout set. And that's right here under cross-validation. You see you can select a specific test set. So if I went here and I had a data set that I wanted, I could select a specific data set for testing. Why would I want to do that? Why wouldn't I just let the algorithm do this kind of recurrent splitting of my data set to do an evaluation? So I'm going to talk about a couple of cases here where that's a good idea. One is predicting the direction of the stock market. Suppose you want to predict the stock market's direction. Basically, you want to predict whether or not a point at a given time is going to be lower or higher than the close of the market. So here, for example, in this little stock chart that I have, we're going to label these points. This block of points is going to be negative because the close of the day is lower. So you would lose money if you bought at that point. So these are going to be our negative points. And then the positive points are going to be, for example, this block of points down here that are lower than the close of the day. So if you bought the stock here, the close of the day is lower, you're going to make money on that buy. Let's say you have information for this market that you're trying to predict for each minute of the day. So for each minute, you have a separate instance in your data. So the thing to note here is that minutes next to each other tend to be correlated, right? These blocks of negative points, they tend to all come at once because in general, the price of the market stays the same over time. It doesn't make big discontinuous movements. Also, the conditions of the market around any given point are going to be sort of the same for adjacent points, right? We don't generally have huge spikes in volume, followed by no volume at all. The market tends to be the same from minute to minute, roughly the same. And so these minutes are going to be correlated in the objective, and they're also going to be correlated in the input. So if you have the answer for minutes, 1032 and 1033, then probably you have the right answer for minute 1034, because these minutes are kind of near duplicates in the data set, right? The minute 1033 is going to be almost an exact duplicate of 1034 because they came at the same time, the conditions were probably the same, the relationship to the closing price is probably the same. And so that means you can trivially predict the value, the class of some minute if you have the minutes next door. So if you have cross-validation holding out a random subset of these minutes in each fold, it's going to tell you that your classifier is near perfect because you've always got these adjacent points that will let you make a perfect prediction. So this is a problem, right? Because in general, you can't predict the direction of the market. In general, that's really, really difficult. But cross-validation is going to tell you that this classifier is almost perfect. And so lest you think this is an uncommon example, let me give you one more example here of somewhere this might happen. This is an example I actually worked on. You're trying to predict the age of a photograph based on things like it's the way the dye is fading and the watermark on the photographic paper and the presence of the type of a border on the photograph. So you can imagine with all these characteristics, you can kind of get a good idea of what the age of the photograph is. And so your training data set has a bunch of photos in it, but they're only from a few dozen people. So what's the problem you're going to have here? The problem is that the age of one person's photos are correlated in both the input and the output spaces. Again, because the person is in general the same age from moment to moment. They have the same camera, they're storing their photos in the same way. So if you know how old one of their photos is, or how old, say, 9 of their photos is, you can probably predict the age of the 10th one. Right? Because it will look sort of the same. It will have the same border. It will have been taken by the same camera, stored in the same way, and taken by the same person. And so probably, you know, they'll be roughly the same age, plus or minus 5 or 10 years. You probably don't have an equal number of photos throughout your lifetime. And so you can do trivially well. You can trivially do well predicting the age of some of their photos if you know the ages of the rest. And then again, cross-validation, if you're just holding out random photos from each person, now you've got an example from every person in your data set. And so cross-validation is going to tell you again that you have a very, very good classifier. And the problem here, right, is that you do have a good classifier for predicting essentially which user those photos came from, right? You have a good classifier for that. What you don't have a good classifier for is predicting the ages of the photos of a novel person, of a new user, of a new a batch of photos that comes in. And the same, you have roughly the same problem in the market prediction case, right? You can do a very good job predicting the points that are adjacent to the ones that you already have. Of course, that's not useful. What's useful is being able to predict when you don't have those adjacent points for new days, for new batches of data. And so this is, you know, a real time to take care here. There are situations that are very common in a lot of cases where data comes in batches. Here we talked about batches of days in the market case, or batches of batches where each batch is a user in the photo age case. But there's a lot of other cases, right? If you have several retail locations in your business and all of your data comes from 5 or 6 of these retail locations, that's another case where your data comes in batches. And a classifier that you train on these batches might not do on these retail locations, might not do as well with a new retail location. And the solution is pretty simple here. You just construct a holdout set for your data of specific points. So basically, you try to hold out all of the user's data from certain users, right? You don't select a random subset of points from each user to hold out. You hold out entire users. Or in the case of the market prediction, you hold out all of the most recent data and you train only on the data in the past. So you don't get this problem where you have information about adjacent points in the data that can help you make classifications, and you won't have that information when you get to production. And so it's possible that you have a problem like this, like you have a problem where the data is split up between users like this, and that it isn't an issue. But when in doubt, you should try this test. And if your performance goes down significantly on the optimal after you've made a custom holdout set and you've selected it here and you've created an optimal, if your performance is significantly worse than when you do regular old cross-validation, you should be suspicious that this is the sort of problem you have where it's going to have trouble with completely novel data. Okay, so that's maybe the scariest little bit is when or not to use cross-validation. That's the place where you can kind of get shot in the foot when you use model selection, or when you're trying to do model selection. And again, none of these things are unique to optimal, right? It's not just that when you use optimal you have to worry about these things. You have to worry about these things no matter what. But what optimal does is it kind of makes all the other hard choices for you about modeling, about how to split your data and so on and so forth. But if you have these problems, now these are the choices you need to make. So these are the kind of only remaining important things after you decide to use optimal or some other automated machine learning technology. And so the last of these is going to be selecting the best model. So it seems like it should be trivial to just predict the best model, right? But performance isn't the only issue. There's a few other things you need to worry about here. If you're retraining the model periodically, will you have the same amount of data? If you're using a very complex sort of model like boosting or deepnets, it won't respond well if you try to retrain it with way less data than you trained it initially. Similarly, if you expect to be getting a lot more data in the future, you might want to use one of those more complex models, knowing that the more complex models will be able to take advantage of that increased amount of data. The stability of the fit. So if your data set changes a little bit, if you add 5 or 10% more data to your data set, do you need to be confident that the classifier's behavior is not going to change dramatically? If you do, you might want to use a simpler model, something with higher bias, something that is invariant to these changes in the data, like logistic regression, if you can't handle the fact that adding a little bit of data might change the model's behavior somewhat dramatically. And then finally, prediction speed. To do logistic regression, you need to do a single kind of dot product, basically. That's the bottleneck in logistic regression. For deep nets, it's going to be thousands of these same dot products. So the difference in prediction speed can be orders of magnitude. So if you need millisecond latency, this is something you might want to consider. And so if we go over here to the finished optimal, we can see that we have a list of the models that were created in the form of this bar chart. Here's the metric that we selected. And basically, if you mouse over each of these, you have the name of the model. And then also you have the names of the models you created down here. You can sort by any metric you want. So if you're interested in the ROC, you can sort by that. If you're interested in recall, you can sort by this. And so here's a good example when I'm sorted by recall of a case where a simple model might be adequate. So maybe you really appreciate that decision trees are very interpretable, right? You need to run a model where you know exactly why it's doing what it's doing, as it does that thing, or a model you can introspect very carefully to see what its exact behavior is. Maybe you really value that in your application. And so maybe the fact that it has 5% less recall isn't that important to you. Rather than using, a 97 tree decision forest, where it's going to be a lot tougher to figure out exactly what it's doing in all cases, you can get, for a small performance trade-off, you can get a model that's much simpler. It's not always about just taking the model with the highest performance according to whatever metric you select. It can also be about taking the model that works best in your application for any number of reasons, speed or interpretability, so on and so forth. And so here's some of these trade-offs you might want to make. I won't go into these too deeply, but basically the more complex models, they tend to be slower to learn and to predict. They have more representational power. So if the thing you're trying to learn is more complex, the complex models have the ability to represent that function. Their performance tends to be higher. So especially in cases where you have that complexity, their error tends to be lower. And then finally, they also tend to be data hungry. So if you want to fit them properly, you need loads and loads of data. Compared to the simple models over here, like logistic regression, they're weak and they're biased, meaning they don't necessarily have the best solution in their repertoire. They're not, they don't have enough complexity to represent a huge class of things. But what you lose in complexity, you get in, first of all, confidence in your solution, stability of the fit. You have a good idea that when you fit a logistic regression model, that's the best logistic regression model you can get. Adding more data or fiddling with it a lot generally doesn't produce big discontinuities in behavior. And then finally, interpretability and logistic regression models, which give you a coefficient per feature or single decision trees where you can introspect them all the way down. The simpler models tend to be more interpretable. So again, if we go back here, there are reasons not to choose the model with absolutely the best performance. And that's why we offer more than one of these things at BigML. because there are a whole bunch of other things, or there are several other things you might want to consider when you're choosing which model to put into production. Okay, so that kind of wraps up the pitfalls of model selection. Again, whether or not you're using OptiML, this will help you do that more effectively. And finally, we get to the bottom here, and we have just a little buyer beware for these automated machine learning technologies. First of all, model selection tends to take a lot of data, right? So you can imagine we're doing cross-validation, so we're holding out some of the data each time we train the model. Internally, deepnets and boosting also hold out some data as a method of preventing overfitting internally. And so we have these kind of nests of cross-validation going on. And eventually you get to the bottom there and you might not have any data left, right? Especially if you have one class that's very rare. If you slice off a little bit of it each time, you're really going to impact the model's performance. Essentially, to do this, to do model selection properly, you need to make sure you have enough data. If you don't have enough data, you might get search results that are not that satisfying. And then the other little buyer beware here is that we, BigML, had to define a search space that would suit most data sets. We had to define a space that would usually give you a good answer, regardless of what data you came with. It's possible that you have like one of these corner case data sets where the right model for your data isn't in there, or the best model for your data isn't in there. For example, if you have a model that responds well to thousands of iterations of boosting, that's not in our search space. We can't do that every time for every person because it's horribly expensive and takes hours and hours depending on the data that you have, and produces a huge model that's not usable in a lot of applications. It's too much memory. And so we excluded that from our search space because its usefulness is kind of rare. But that means that if you have data that demands that sort of model, there's no reason that you can't just go out and do it. That's why we offer you this sort of control over the platform. If you don't have a model that's in the search space that we define, you can still go out and get it. You're still able to parameterize these things by hand and construct the model that you need. But I would say that the search space we've defined, I would say almost always contains something that's nearly the best thing for this data. So there's almost never a need to kind of go out and explore on your own unless you're fairly sure that you have data that's very odd. Okay, so that ends the substantial portion of the webinar. You'll note that we've done a whole bunch of blog posts. We've got a whole bunch of documentation that you can come and take a look at if you're interested in more about OptiML and different use cases for it, how it works under the hood. In particular, the post that we just posted this morning, the one that I wrote, goes over again, maybe with a little more clarity, a lot of the points that were in this webinar. So you can use that for reference. Also note down here that we have a what's new page. One of the things that's new recently is prediction explanation, which enables kind of decision tree style interpretability for a given prediction for any model type. So that can be cool if you're interested in the explainability of predictions. You can take a look at that. In general, keep an eye on that page. We tend to post whenever we've got any kind of minor improvements to the service that aren't worthy of their own release. We tend to post them there. So do keep your eye on the what's new page.